Alright, another draft physics presentation. Lights are all wrong. Who broke the lighting? But anyway, somebody, conspiracy, something or other, blah 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 blah. Anyway, get to the point. Yeah, so the cranky guy posted a link to an image video, you know, which okay, it's better than nothing. But you probably should post the link to an image file posted somewhere or something. I mean, I could give you some server space if you know how to FTP or something. But anyway, it's just this image file isn't the greatest way to read, the text or to see exactly what it is you're arguing. So anyway, I'll get to that. Get to a comment first, I suppose. So not too many comments on the video where I explain what I say is happening, and no relevant counter arguments to what I propose to be the truth. And I'll go over that a little bit again. So anyway, the FBI guy says, "Hey, fuckstick, you said you wouldn't do the laser bending experiment because the difference would be too small to detect." So that's the experiment where you shoot a laser across, hundreds of meters and try to detect how much movement there is in the laser. I said the haze the laser creates is so big, the divergence of the laser, that you can't detect a little tiny difference in its center. Now you're saying the laser would miss the target completely. No, I'm saying in the interferometer it would. I don't know, you can't separate these two. You're literally too stupid for compost. Well, you're literally too rude to be worth the trouble. So, fuck off. These people. Alright, so then this guy is asking to do the wager thing, asking for more information. Wait, maybe you ought to wait and see how this ends with Adrian Farley, because he seems to be conceding something here. So he says, when I said the up velocity, I meant the y component of the velocities of the photons going the sideways paths, which isn't really very helpful. So anyway, I'll read what he says at the end here. However, if it's me grossly misunderstanding something, then I apologize, just trying to help. So that's kind of a weird concession to something. I don't know, for all this rhetoric. So in some way he's trying to say that I was saying that what he says is a difference between 79 is not 54 millimeters, and I would argue that I don't think that's accurate. So I'll go back to the image. He's saying that somehow this is 54 to this line here. I don't know what this line has to do with anything. We're talking about the point where it stops, not this line. I don't know what this line would have to do with it. Obviously, in the moving experiment, both legs move a longer distance, so they'll take longer for the event to happen in the moving frame, but both legs will take longer, the exact amount longer. Both legs will be still equal. We're talking about the length of the legs. We're not talking about comparing a moving one to a stationary one. We're talking about whether there's a difference in the moving one between the length of the two arms. And that's the part that's relevant. So I don't know why you're still arguing a point that isn't my point. So clearly I was arguing that the two distances were essentially the same between where the photon begins and where it stops. And yes, it is a little shorter, but the trick is, well, let's look at the animation again. I really hate doing this over and over again, right? You can see that, right? Yes, okay. I mean, I'm not responsible for how it plays. One of the weird things is, so notice in this run, the photon's moving a certain speed and then it moves faster going back. Now the whole point of having this moving thing and everything else is to keep everything constant. So the speed of this photon should have never sped up like that. So what's the excuse for speeding that photon up? That's another thing that's just totally inappropriate here. It's going a consistent speed and then it bounces and speeds up. So that's wrong right there. So besides the obvious things, I say that photons don't move sideways for free, which he seems to be conceding in his drawing. So again, we'll go back to his drawing where, so he's emphasizing some 79 doesn't equal 54, so he has that in big text. And that wasn't my argument. My argument was the height was the same as the length in this circumstance. In the lower image, the lengths are equal. So we already know that those are equal lengths. And my argument is that we know when the photon stopped that the length of the bottom leg was almost the same as the length of the top leg, which couldn't possibly be true for anything in the range of half the speed of light. Now he's conceding that this is probably 40% of the speed of light. Well, 40% would make some difference, so we would change the 8 into like 7. So the total length would be something like 9 3/4 instead of 10 3/4, that kind of thing. But it's not going to change the basic flaws that exist. And one of the flaws that exist is the light never reaches the mirror. You can't hit it. So I guess I'll go over that part. And so what you can see in this image is that in the upper image he has with the 79 there, he says 136 total units so far, and he has a point. And then he goes 135, 35. So they're equal at these two locations. And clearly you could surmise that this target's going to move towards it. So when this one bounces, it's only going to move this distance before it hits the mirror. And likewise, this one's got to go this whole distance yet to hit the mirror. So the total's going to be exactly equal. If he did it all the way through, he has them equal at this point. So you know that they've already traveled 135 to get to these locations. And nothing's going to change when the mirror moves to this location for the final product. These distances will be the same. This distance will be the same as this distance. So the distance to finish the downward leg is going to be exactly the same for finishing the across leg, which means both lengths are the same. So it's exactly as I stated. So I'll attempt to draw some of that. So I mean, if you want to read this, I don't know. He talks about the speed of particles, and I don't know why he just didn't say the speed of light. I just don't. This isn't about the speed of particles. It's about the speed of light or the speed of force. It's about going a specific speed. A constant speed, a speed that has to be constant for lots of reasons. Alright, so what do I want to do? Yeah, so go look at it yourself. Like I say, he doesn't seem to concede anything, but he sort of concedes something, so I don't know where we are exactly and what he still asserts. The important point I guess I wanted to raise was what he is apparently conceding is that he is going to account here for the actual distance the photon travels. So now he's counting for the actual longer path. He doesn't get to go this straight up and down 79 thing. He has to do this thing, and that's going to be a much longer path. So at least he's conceding that, which is something. Anyway, it appears he's conceding it. Alright, so that's probably enough, and so we'll do some video and try to keep this briefish. I just want to do some response to the fact that he did provide the video, so I'm gonna, I appreciate it, the clarification. I had already surmised in the earlier video that it can't be half the speed of light, because I already stated how it doesn't look like it's the proper number of 8 units long. So one of the arguments I make the first argument I'm going to make is, as I've stated it previously, these photons don't go this way. They go this way. So the experiment's broken right from the start, because the mirror moves, the photons don't. They go straight and they just fly right where the mirror used to be, and that's it. It doesn't work. Once you start moving at any kind of speed that gets you further than the distance of the mirror, once you have a speed where this mirror moves enough of a distance in this whole time, once you get like 1/10 of the speed of light or something, probably less than that, this photon never hits the mirror, it just goes straight. And then even if we allow for the photon to go forward into the future kind of argument, I'm going to argue that it always ends up being the same as the length this way. So we have the length this way and then a little bit going back, right? So we have the idea that the photon goes here, hits the mirror, and then comes back some distance, and it's 50-50 when it's standing still, and it'll be some other ratio. As you add velocity, it goes 51-49, blah 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 blah. And when you're at half the speed of light, you ended up with 2 3/4 versus 8. So you went 8 in one direction, 2 3/4. So it comes down to what does that come out as percentage wise? This would be like 20%, and this would be 80%. So it'd be like 80-20. At half the speed of light, you're at 80-20. And the argument I'd make is no matter how you do this ratio, this forward distance will always tell you where you have to be to hit the mirror, where you have to hit the mirror. The mirror will always be halfway. So if this number is, like in this case, 40% the speed of light, well, 40% of the speed of light gets you a line that would be a little shorter, so let's say 7. You would have to be at 3.5 to be able to hit the mirror and go this way. So this, no matter how long you make, so if I make the line the same length as in his diagram, you know, the standing still model, where the two lengths are exactly the same, there's 0, okay, in terms of your angle is straight up and straight down. And as you make a little differences in this length, then you just start separating this point where you can hit the mirror. The point where you'll be able to hit the mirror starts increasing. Proportional to the distance. I guess I should get another proportional thing, maybe. So maybe that's not true. I have to think that through some more. Yeah, any movement in the mirror is going to require you to go into the future to hit it. So, so I'd say even if I conceded that it was possible that photons automatically know to go forward, they have to go forward at a specific point to be able to hit the mirror, because they come up short. So if you look back at his diagram, you know, he has the line that goes. Sorry, this drawing's a little shaded, but it's just the way it turned out. He has it drawn like this. It hits the mirror moves here for whatever reason, and then he stops here for whatever reason, and he says this distance is somehow significant. The point is that when it goes this way, the photon at the speed of light reaches where the mirror is, and it's still here. So it doesn't hit the mirror at the location he had to hit it in the mirror, because it still comes up short at the speed of light. So even if I conceded that photons can go forward, they have to go forward to a specific location, you know, a very specific location, and that location will not match where the beam splitter will be. It doesn't go to this perfect location where you can go up and down like this. That's not going to happen. Then your photon is either going to be ahead of your mirror or behind your mirror, but it won't be where it has to be to get to the beam splitter again. So that's another flaw. So first flaw is photons go straight up, they don't go forward. Second flaw is if they do go forward, it's a longer line and they can't travel the distance at the speed of light in time to get to the mirror when you have it where you want it to be able to get to the beam splitter. You actually have to go forward to some other location, and that'll take you where the beam splitter is not going to be. So it's another reason why the experiment breaks. So those are two fundamental reasons why it can't work. And still, my argument is no matter what time you make it, as shown in his very diagram, like I said, we go back to it, he says 135, and the locations are, here's the beam splitter is going to, beam splitter will be at this location. The other thing is here, and you can barely see that. try to do it in red. I mean, maybe you can see it. Well, let's redraw it. Better location. Why it's too much shadows. Everything's a little bit wrong this time. Oh, I had to fix the light. That was true. Anyway, still wrong. Alright, so he did this thing, and he stopped here. The beam splitter was here, but we know it's going to be here. And the other beam was here at the end, and we know the beam splitter is moving towards it. So these two, so they were both at 135 at this location. And these two distances have every appearance that they're going to be exactly the same. And so you'll end up with the two legs having exactly the same total length, which means they have the same exact total time, which means you can't use this device to measure a static leg and a moving leg, because both the legs are moving and both of them have the same time dilation. Both of them will take more time to complete the processing through the experiment, and both take exactly the same extra amount of time. So those are 3 points that are important points. So if you have arguments defeating any one of those points, first, the photons travel straight, they don't move into the future. Second, your longer line can't be traversed in the time you're allowed to get to the mirror, so you can't hit the mirror. And third, the totals will add up to being equal in terms of total distance and total time traveled by the photons, even if I allow your photons to be shot into the future. And the fourth little argument is, if you look at the animation, okay, a fundamental flaw in the animation is the fact that the photon's moving this slow speed and then it speeds up going back. Can't do that. Can't be accurate to have that change in speed. A change in speed is a breaking of the program, the math. It's a huge flaw. Alright, so that's enough. So that's 4 good points that I don't think you have a rational answer for. And Hoffiday's relativity answer, in my opinion, is out of the context. This is Michelson-Morley. This is 15, 20 years before Einstein's theories of relativity. It's before anybody knew about frames or time dilation. And you just can't use those as excuses for why Michelson and Morley thought these two legs had different periods. That it would take a photon longer to travel one leg than the other. Why did they think so? Why did they think photons move into the future for free without it taking any time? Why did they think that this hypotenuse can be traversed by a photon in the same amount of time as this straight line? I mean, any idiot, okay, any idiot can see that this line is longer than this line. Any idiot can see that. And why didn't Michelson and Morley see it? Fair question, in my opinion. Because it's the whole reason why they thought there was a time difference in the two legs. Without this pretending that you don't have to account for the forward motion in the perpendicular leg, where's your time change? And this really goes for the LIGO experiment too, because they're still assuming there's some sort of difference in the length of the legs. And this, I think, demonstrates there is no difference. You can't stretch one without stretching the other in practical fact. I'll have to be careful about that because they're using bending, contracting space, which is a little different. Contracting space isn't about photons travel time, so it's not really about the LIGO experiment moving. So maybe they can get away with it somehow, but I doubt it. It's still probably bullshit. But anyway, it certainly can't be used to measure ether drag. because the two legs don't have a difference in time for successful navigation. They both move the same speed and they both move the same distance. The photons travel the same distance, and they should travel the same speed, obviously. So, enough. Till next time and such.